So, welcome to lesson 10 of your electricity unit of work, and today's lesson is on electrical power. So, to begin with, can you pause the video and have a go at the first set of knowledge check questions on this lesson, which are purely true or false questions, reviewing content from previous lessons. Which is true, which is false. Right, if you've had a go at that, you've unpaused the video and you're looking for answers. So if we just run through them quickly. UK mains voltage around 240 volts. False, it's about 230. AC supply frequency is about 60. False, it's about 50. Live wire is brown. True. Neutral wire is blue. The earth wire is red. False, it is yellow or green, sort of striped. The live wire is most dangerous. True. The neutral wire carries no current. False, it's not quite, it's like a zero voltage, but it can still carry current. And the earth wire has a voltage at or close to 0 volts. True. Good. Right, let's move on. So, as you'll see, we are going to be looking at electrical power today. So if we just read through the paragraph together. Now, electrical power is when an electrical device is used, the current through it transfers energy from the power source to the appliance. The unit of power is the watt. You should recall that power equals energy transferred divided by time. Now remember, you might see that written as P equals E over T. Remember that when you're talking about energy is always measured in joules. For circuits, there's a more useful version of this equation. The energy transferred to an appliance per second equals the charge flow per second times the energy transfer charge per unit. Now, it can be a little confusing, that definition. So if we simplify it to this is the important thing to try and remember today. Electrical power is talking about the rate at which energy is transferred per second by an electrical device. So this is worth making sure you've got written down in your annotations just to try and understand this concept. Now, the power equation is given by power equals potential difference times current, or P equals VI, okay? Now, we will come on to this later, but you can make a note of it now, in that power can also depend on the resistance of a component in a circuit, so how easily current can flow through it. And there's a second equation that we'll come to later, that power equals current squared times resistance, or P equals I squared times R. But for now, we're just going to concentrate on this one. So make sure you've made a note of all those annotations. Pause the video where you need to. And if we have a little look, so the checkpoint question down the bottom here, state the equation for power in a circuit in terms of V and I. Pause the video, take it away, turn to a separate page. Can you recall it from memory? If you've unpaused the video, hopefully you've got P equals IV, power equals watts, current in amps, and potential difference in volts. Now there's an example question here. Calculate the electrical power supplied through a 230 volt electric motor when the current is 2 amps. So what is the power when your voltage is 230 and your amps equals 2? So you've got 230 times 2, which gives you 460 watts. Remember that W is for watts. So we've got the same question down here as an example. You'll see that power equals 230 times 2 equals 460. Let's try and look at it in a little bit more depth. There's a couple more examples. As you'll see. A torch lamp that has a current of 0.25 amps passing through it when the potential difference is 3 volts. So remember, power equals V times I. There's your I, there's your V. So that gives you 0.75 W. And remember that W is watts. A 12 volt lamp, there's a 3 amp current through it. P P equals VI, so 12 times 3 equals 36. And then a resistor has a current of 0.2 amps passing through it with a potential difference of 6 volts. So again, we have voltage, we have current. So we don't know power. And we know that power equals voltage times current, so times them together, gives you 1.2 watts. Good. Right. Have a go yourself. So pause the video for me now and have a look at this table. Now remember, whenever you are using an equation, you might have to rearrange it. So there are 3 iterations of this equation that are worth remembering. Power equals current times voltage. To move the V over to the other side to get I equals current equals power divided by voltage. And thirdly, voltage equals power divided by current. So you've got current in amps. Remember, we also use an I to represent current. Voltage, V, and power in watts, P. So can you pause the video and use those 3 pieces of information to try and work out the answers to all of them? Right, hopefully you've had a go. So you've unpaused the video, so let's go through the answers. So first up, potential difference and current, which means you need to do current times potential difference would give you 92. Mark it if you've got it right. 230 times 0.4. You've got power and you've got current, so you need to divide. So if you divide those, 18 divided by 1.5 should give you 12. You've got power and you've got power and you've got potential difference. So P over V, you divide, give you 2.6. You've got current, you've got potential difference, so you times them, and that should give you 805. Again, divide. 36 divided by 3 would give you 12. And then power divided by potential difference, 2.4 divided by 7.2 should give you 0.33. Mark them if you've got them right, correct them if you've got them wrong. Right, let's have a look at the next section where I might have to apply this a little bit more in depth. So, applying multiple equations. So let's work through these together. A current of 0.25 amps is passed through a 100 ohms resistor. What's the potential difference across the resistor? So use Ohm's law. So, oh, sparkly pen there, not quite the one I wanted. So we don't know V. Ohm's law, V equals IR. So what is our I and what is our R? So I times R should be 0.25 times 100, which if you'll see should give you 25, which if we look at our answer, it'll be 25 volts. The electrical power supplied to the resistor. So we know that power equals current times voltage. Right. It's a 2-part question, so we might need to use bits from this question in here. So, what's our current? That's right, 0.25 amps. What's our voltage? We've just worked it out, haven't we? 25. Times them together, give you 6.25. Now, if this is power, it's not amps, it's not volts, it's watts. Good. Make a note of those as we go through these examples. Calculate the current through a 230 volt 1000-watt electric heater when it operates normally. So hint, rearrange P equals VI to make I the subject. So P equals V times I, give you I equals P, need to move that across, divided by V. So can we put it all together? What's our power? Hey, what is our power? 1000. What's our voltage? What's got a V next to it? 230. Divide them. Give you 4.35 amps. And as you'll see, got the same answer there. And then calculate the current. Where am I? Calculate current through each lamp. So a mains lighting circuit has four 230 volts 100-watt lamps connected in parallel to each other as shown in the diagram. The circuit is protected by a fuse. What is the current? So we've got a V, we've got a P, and we want to know an I. So in other words, I equals P divided by V. Slot the numbers in. 100 divided by 230. As you'll see, take off a 0 here, same as this. 0.435 amps. Good. Like so. Right. So, we've had a little look at that. Now, let's have a little look at the other equation we were talking about a couple of minutes ago. Power when involving resistors. So let's read through this section together and then have a look at the annotations I've added and add them into your own notes, please. So, when a current flows through a resistor, it has a heating effect. The resistor heats the surroundings so the energy supplied is dissipated to the surroundings. So remember, heating effect is when the ions and atoms of metals and components vibrate more, and the electrical energy that's being carried by the electrons is transferred to thermal energy and then it's lost to the environment. That's what that means. So to calculate the rate of energy dissipation, so remember, energy dissipation is loss of energy. There is another version of the power equation. P equals VI, but since V equals IR, replacing the V means that power equals current times resistance times current. So that gives us our equation. That's where it comes from. Power equals current squared times resistance. So this is a second version of the equation we might have to use if we are given resistances in equations instead of potentially voltages. So the point here is that electricity is transmitted at high voltage and low current because less energy is wasted by the heating effect when current is low. Now, if the current is halved, then power is wasted a quarter of what it was before. We will come to this in a later lesson, but this is important in the transfer of energy across the national grid. So we'll come to this a bit later in this unit, but it's worth just noting that why this is important, okay? So make a note of those annotations as well. But this type of equation is when you get given R in a question, not necessarily a V. So you might have a question such as the one below. Calculate the power dissipated in a 5 ohm resistor and current is 2 amps. So 2 squared times 5 gives you 20. So if you do the checkpoint question, just pause, turn away from memory. What's the equation for the power of circuit in terms of I and R? Pause, look away, unpause. Power equals I squared times R. And those are your units of watts, amps, and ohms. Right, let's have a look at a couple of questions together and then you can have a go at some yourselves. So, Power in a resistive circuit. In the circuit shown, select the correct equation and calculate the current through each resistor when R1 equals 3 ohms and R2 equals 6 ohms and the battery supplies 12 volts. Now, I1 and I2. Think about Ohm's law. So, for Ohm's law, V equals IR, which means I equals V divided by R. So, for current 1 in resistor 1, our V is going to be 12, isn't it? And our R is going to be 3. It's 12 over 3. Whereas for I2, our resistance is 6, because our second resistor has a resistance of 6, whereas our potential difference is still 12, so 12 divided by 4 would give us 4 amps, would give us 2 amps, as you'll see. Those match up. Now calculate the power dissipated in each of those resistors. So, talking about resistors, so P equals I squared R. Okay. So we've been given current, we've worked out current, and we've got resistance as well. So, for resistor 1, P, what's the current for resistor 1? It's 4 amps, isn't it? So, let's have a look at this. So that gives us 4 squared times, what's our resistance for resistor 1? 3. As for resistor 2, we should have 2 squared times 6. So 4 squared is 16 times 3. 2 squared is 4 times 6. Should give us 48 watts. Should give us 24 watts. Good. Now let's just have a look at the second question here. Calculate the power of the battery. This is the parallel circuit and the individual currents add up to the total current. P equals VIV. So, our voltage. Our voltage, same one, same circuit. It's always going to be 12. Calculate the power of the battery. Add the individual currents. So what are our individual currents? 2 and 4, aren't they? So I equals 2 plus 4 equals 6. So P equals I times V. Equals 6 times 12. Give you 72 watts. Good. Right. Your turn now. So, again, same idea as before. Might need to rearrange the equation into one of these 3 iterations. Power equals current squared times resistance. Resistance equals power divided by current squared. Or current equals the square root of power divided by resistance. So pause the video for me and simply have a go at seeing if you can fill in the blanks for each of these using one of these 3 equations. Okay, so pause the video and do that now for me. Right, should have had a go at that. So unpause the video. And your answers are as follows. Mark them or correct them as you need to. 225, 32, 2, 0.2, 15, and 1000. If you got any wrong, if you weren't sure, go back to these and make sure you used the correct one. So were you being asked to work out R? If that was the case, you'd use this one. Were you being asked to work out I? If that was the case, this one. Or were you being asked to work out P? If If that was the case, this one. Remember on this one, if it's in brackets, Bidmus, from your maths, do the brackets first and then do the square root. That might be where you got wrong as well. So, last little thing here I want you to have a go at. Again, pause the video, go back to those three versions of the equations and see if you can come up with the answers to these. Right, hopefully you unpause the video because you have had a go at these. Let's go over the answers now. So, P equals I squared R because we're looking for the power rating. So that means we need 1.2 squared times 5, which if you worked out comes at 7.2 watts. There you go. I, what does I equal? So look back at those equations at the top. I equals square root of P over R. If you put it in a bracket, that means you have got square root of 800 divided by 50. Should give you 4 amps. And then R, if you look back up, equals P over I squared. So it would give you 1,200 divided by 5 squared equals 1,200 divided by 25, which give you 48 ohms. Don't forget, power is watts, current is amps, and resistance is ohms. Good. So you've had a go at those. Now, check I've got the right. I missed a bit. Now, what I'd like to do, come back to these questions up here and have a go on the notes page. Attempt as many as you can. Remember, you need to use one of two, either P equals V times I or P equals I squared times R. So for these two, I'll be thinking about the first one. And for this one, you want to be thinking about these, okay? Pause the video, use spare scrap of paper, use some notes, notes page, see how many you can have a go at. But just remember, you need to convert your units if you're not sure. Remember, if you've got milliamps, divide it by 1,000. Kiloamp or kilowatt, times your number by 1,000 to convert it, and megawatt, times it by 1 million. So don't forget to convert them into watts, amps, and ohms. Those are your units. Anything that's not in those needs converting. Pause the video, have a go at as many of those as you can. Once you've done that, I'll show you the answers. Right, hopefully you've had a go at those. So, rather than just going through every single one individually, I'll show you the answers on the page below. So the questions you are looking for, question 4 wasn't on there. So, mark your answers. Did you get them right? Pause the video, go through your questions, mark and correct anything, and then change it if you weren't 100% sure on it, and give your teacher an email if you need to. Right, last thing. Can you finish with the knowledge check questions on the last page of this lesson, please? Once you have done that, we'll go through them to finish. So pause the video and have a go at the knowledge check questions. Right, knowledge check questions finished. Mark them, correct them as you need to. Power is in watts, resistance in ohms, current is in amps. I equals P divided by V. V equals P divided by I. Equation for potential difference is V equals IR. Equation for charge, Q equals IT. Current times time. Equation for total resistance, R1 plus R2. And then just a bit of chemistry to remind you. What do you call a row in the periodic table? Call it a period. What do you call a column in the periodic table? Call it a